So we're going to turn our attention back to the concept of reaction rates and specifically rate laws. Let's start with a generic balanced chemical equation where we take two reactants, A and B, and they form a complex AB. And I create three experiments to look at the reaction rate, so three reaction rate experiments, and it yields the following data. You're obviously going to have to hit pause for a moment as you create this table. But let me talk us through this. I'm assuming that you've come back and you've written this all down so far. So I have three different experiments that I'm going to run, but I want us just to simply focus in on right now the first experiment. And in this first experiment, I'm going to start off with a solution of A that is 0.750 m, and solution of B, which has a concentration of 0.750, and again, this is molarity. And so that means they're going to be the exact same concentration. And don't forget, the brackets indicate concentration. So when I say initial concentration of A, that's how you should read that, initial concentration of B. And then the rate that we're looking at in this fourth column over here is how quickly the concentration is going to change over time. And so in this case, you're going to have a 7.00 times 10 to the minus 5 molarity per minute. Okay, so that's how it's going to change. That's how quickly that's going to develop. And then that's the AB stuff. That's how quickly that's going to develop. And then I have a second set of data. And for this one, you can see that I've decided to keep the concentration of B the same, but I doubled the concentration of our A reactant. And when I did that, you can all see here that it actually doubled the rate in which AB is formed. Okay, let's take a look at our third experiment. And you can see in this experiment, what I've done is I've decided to go back to my original concentration that I had for my A for this third experiment, and I decided to then double the concentration of the B reactant solution. So you see it goes from 0.750 to 1.5. So what you want to do is always compare each of these successive experiments to the first experiment. You don't want to compare 2 to 3. You want to compare 1 to 2 and 1 to 3 when we're judging these rates of formation. And in this case, you can see that rather than just being the 7.00 times 10 to the minus fifth rate, I have 28.0 times 10 to the minus fifth. So a much higher rate you can see in this situation. So the question I would have for you after giving you a table like this is, what is the rate law for this reaction? And if I do a generic rate law, let's just set it up without putting in the actual exponents first. So you can see here, this is our generic rate law. And I don't need you to determine the K yet, but I will have you determine the K in just a moment. We have the concentration of A, solution A, and the concentration of solution B. And what we want to do is figure out what these exponents will be to make this data jive, okay, to make all this data work. So what do? When you go back up to here and just look at this data, we can see here that we have an initial concentration of 7 times 10 to the minus fifth, and that in this situation where we actually double the amount of our A piece here, we double the rate. So if we scooch down here and take a look at that, if I double the A, in a sense, if I put a 2 in front of this A to that concentration of A, because if you would assume there's a 1 in front of there for the initial concentration, so here I am, I'm doubling it for our experiment number 2, and you can see that right here, doubled that. Well, what does 2 have to be raised to in order for the rate to double? I think you all understand that 2 would the only way that you could make it double the rate is if 2 is raised to the power of 1. So in fact, I can go ahead and erase this x here, and in its place I can put a number 1. So let's just go over that again. Let's just make sure you understand this. 2 raised to the 1 is 2, which will have an effect of taking this entire component on the right side of the equal sign. It'll multiply this whole thing by 2, which obviously is going to reflect in the rate being multiplied by 2. Okay? Now, so we know what we're going to have here with respect to A. We have a first order rate law with respect to A. But let's see what the rate law would be if we have B. And by the way, you don't keep the 2 in there. That 2 was just hanging out there to help us out moments ago. But we can erase that and just leave the exponent of 1 there over the A. How about for B? I think you can all see here that when I decided to double the B concentration right there, when you compare the rate when we had it before we had it doubled to what it is now, you can see here that this is 4 times faster, right? 7 times 4 equals 28 times 10 to the negative 5, right? So we have 4 times faster. Now, if we double the concentration of something, we're going to do the same thing here. We're going to have the 2 in here in front of the B because we're doubling it just like we did moments ago for the A. And yet, in order to have something, and we keep the A as a concentration of 1 in front of it, because remember, we're not changing that one. That one remains, as you can see here, as the 0.750. So to make this rate be 4 times faster than the original rate, because that's exactly what happens, it's 4 times faster than this one right here, what do we need to raise the 2 to in order to make it 4 times faster? And again, this isn't really difficult math here. All I need to do is replace that y with a 2. So 2 raised to the 2 is 4, which makes this whole thing here multiply by 4 to make the rate 4 times faster. So, and let me go ahead and erase this doodad in here, get rid of the 2 there. So we can see here that we have a second order rate law, because we always name it by the highest order that we have going here, to describe this reaction of A plus B leads to the product AB. So that's a pretty simple process. Now, what about figuring out what my K value is? That's an important thing here. Well, it's not that difficult once you figure out this rate law, because then you just take one of the lines, either experiment 1, 2, or 3, and you plug in the data to get this. So I'm just going to arbitrarily, I'll take the first one here. Should I take the first one? Yeah, why not? We'll take the first one, and if I plug in that data, it's going to look like this. So you can look and see what I've just done here. I took the rate because that's exactly what we're looking for, right? This shows us the rate of the AB formation, and I put that right here in this place, so it's right here below in our rate position. K is what we're looking for, so I keep that as K. And then I have my 2 concentrations, and my initial concentration for my A was 0.750, which is why I have 0.750 there. I make that raised to the first power because remember that's our rate law right there to correspond with the 1 to 1. And then I take my concentration of B, which is also 0.750, and I put that right in here. But this one gets raised to a power of 2 because our rate law had a 2 there. So when you do this, when you calculate this out, you find out that when you solve for K, I'm not going to go through that process because I think you know how to solve for K in this situation. I get a K of 1.66 times 10 to the minus 4. That would be my K. And keep in mind, this is very important, that K value is going to be very temperature specific. So this rate is not going to happen with the same K value if it was at 90 degrees C as opposed to 0 degrees C. It's going to be a very different K. So K is very temperature dependent. You got to make sure you write that in there. Temp dependent number. Because obviously these rates of reaction are very temperature dependent. Okay, let me pause for a moment. Okay, let's take a look at this data set now, set up in the exact same way, and I want to see if you can figure out what the rate law is for this based on this data. So I'll go ahead and pause it, see if you can work this out, and then come back in to see the solution. Okay, so I hope you had a chance to do it. You probably cheated and just kept playing this thing, but that's okay. So if we take a look at the generic thing, we just need to fill in the x and the y once again. In this case, though, notice that when we change the concentration, we double the concentration of B, it has no effect on the rate of formation of AB. When that's the case, the only way you can do that is to have this raised to the power of 0, which essentially makes this whole expression 1, and therefore makes this whole thing not change. The only thing that it's dependent on then is the concentration of A, not B. So you can have an order of 0 up there. And then if you look at the comparison between 1 and 3, you can see here that we've gone from having 4.0 times 10 to the minus fifth to 16, so it's 4 times bigger. And if you double the concentration in this case, and again, you could just put the 2 in there. 2 raised to the second power is 4, which is why the rate increases by 4 times. Let me just erase that one little bit there, right there. So we have that as our new rate law. We could do the same thing to find our K as we did in the example above by plugging in the initial rate of AB as our rate and plugging in the initial concentrations for A and B, solving for K, and giving us the K value there for that particular temperature. Okay, so pretty straightforward for these ones. They do get a little bit more complex, not too much more complex. We don't want to wreck your brain. But you can imagine situations where instead of just doubling the concentration, perhaps I'll triple the concentration and show you how the initial rate of formation might change as a result of that. And so far I've only shown second order. It could be that you have a third order where something increases. If I double the concentration, then perhaps it multiplies the whole reaction rate by 8 times, 2 raised to the third power. All right, so keep that in mind that we can have exponents of any number, and they could be 0, 1, 2. They're going to be whole numbers, so they'll be integers, just to keep things simple for you. Okay, good night.